Okay, guys, so we'll start now. All right. So I'll just take a quick review. So, we had this two security model earlier, right? Just one
Yeah.
sec again. Put them to my pen here. Oh, now suddenly it's gone off. Okay, so we had this two security model, right?
Yeah.
DST is mu T STDT plus sigma T STDBT. And then we had this money market, right? And then we said, okay, can we find a portfolio? Can we find a change of measure under which the stock price gives the same rate of return as the risk-free rate of return?
And Prof, the
So,
money market part is the risk-free part, right?
yeah,
Okay.
exactly. Okay, right. So we're looking for, you know, this is the kind of change of measure that's allowed to us by Kurzanov. Uh, so we plug that in here instead of dBT. And then we see that if we choose a alpha t to be mu t minus RT by sigma t, and the only condition we need for that to work is that sigma t should be strictly positive, then indeed under the new change of measure, the stock price has the same drift as the risk-free security. But really what we are looking for is discounted stock price. So let's do that here. So this is again our risky security. This is our discount process now,
Prof,
right?
we can
RT
only
is,
see your application to Guzmanov's slide, like slide number 30.
oh, so I moved on. So what's going on? Why is that an issue?
Can you try to reshare the screen if possible?
Let me do that.
Yeah.
So right now it's not even sharing. Should I just log out and come back in?
Yeah,
I
yeah,
can
I
do,
think that would. Yeah, yeah,
let me do that. Let me do that, yeah. Because you're the host, right?
yeah.
And this is my own account, right?
Yes.
ठीक है.
So sorry for the inconvenience, guys.
Right. Oh yeah, no, I was not doing this advanced spell. Cable here. Yeah, so now I can see my screen. Can you see it?
Yeah, 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 it's visible. Yeah.
Yeah. Okay, now it's
Your
moving
camera
as
is
well.
off, bro.
Okay, let me turn that on as well.
Yeah,
All right,
perfect.
good.
Yeah.
ठीक है, so far we are good. So the point was, yeah, then we choose our alpha t in the following manner, and we can do that as long as sigma t is strictly positive everywhere. And then our stock price then has the right drift here under the change of measure, right? Uh, but really, we are looking at discounted stock prices. Those guys should be martingales. So we again look at our risky security here, and now we look at our discounted process. So RT is this quantity right here. It satisfies this differential equation, right? And now we have that DRT ST is RT DST, ST DRT, and DRT DST. And because DRT is a finite variation process, this guy is going to be 0. So this quantity is just RT into DST, which is this quantity right here. We just plug this back in here. And DRT, which is just this quantity right here from here. So from all of this, you see that. What happened?
I think your screen stopped sharing for some reason.
It just wanted me to trust. So now, okay, what do I do again?
Wait, did something happen on your computer? Oh, yeah, it's
It's,
visible again. It's
yeah, no,
visible.
it asked me if I trust and all that. I said I trust. Okay. Okay, so ठीक है. So this is where we are. So we are at this point right here. All right, again, we use alpha t as before.
Hmm.
So you can see just by using alpha t, bringing it here, mu t minus RT by sigma t, mu t terms going to get cancelled, RT terms going to get cancelled. Right, so we bring this in here, what we get is drtst is now a
Hmm.
stochastic integral. So it's a martingale.
Yeah.
Again, I'm not, I'm just assuming that our sigma t is nice enough and RT is, well, RT would be nice enough so that, the stochastic integral is indeed a martingale. Some mild conditions are needed.
Hmm.
In particular for stochastic integral to be a martingale, the integrand should be in H2. But
So
we are
just to be clear, we just need the absolute value of the thing squared to be finite, like the integral of that, right?
yeah, yeah. Well, I mean, in this case, we need 0 to t RT sigma t, sorry, ST square dt expected value is less than infinity.
I think we did something
And
similar in the assignment when the integrand is like doubly integrable, then it's a martingale.
Okay,
a small question. So the square comes in because you first use Ito's isometry first, and then you get
that,
this.
that's right. Yeah.
I see.
I mean, this is just indicative. Huh? You'll require a much more elaborate discussion to get the technicalities right. So for an undergraduate course, we decide to focus on, not focus on these things basically.
Prof, can you go to the
I see.
previous slide, slide 32 once?
Hmm.
And here, what are we defining the DRT term? Like, what's the intuition behind it? How is it related to the market price
It's the
differential?
discount rate, right? It's like if I'm getting 1 rupee at time t,
Hmm.
what's its value at time 0?
Okay.
How much
And
money do I need at time 0 to get 1 rupee at time t? That's the right way to think about this.
okay.
You know?
Yeah.
So this much money will become 1 rupee in the money
Yeah.
market at
Yeah.
time t.
Makes.
Okay. All right. So this was our change of measure that we got. If we got it through this as the likelihood ratio. Okay. And then we said, let's look at the replicating portfolio, the self-financing portfolio process. So that's investing 80 in the risky security and
And
the
then
remaining wealth in the uh,
risk.
money market. Yeah, risk-free security.
Okay.
Okay. Then we do DRT XT, that's RT DXT plus XT DRT plus DRT DXT. This term is again going to be 0 because RT is finite variation.
Hmm.
So then you have these quantities as before. You keep on simplifying because I guess the RT term is getting cancelled. AT term is also getting, well, what's going on? Yeah, this RT term is getting cancelled, right? I'm not, yeah, with this XT term here. And then this, what remains is in the following form. You take AT outside, and this quantity is just AT TRTST. And that we know is ATRT sigma TST dP delta D. Because DRTST we must have done over here,
Yeah.
right?
Yeah.
Do we need to go through this slowly or you can kind of just accept it?
I think we already saw this earlier, so you can go at
Yeah.
the same pace you're going.
Yeah, we saw this earlier, Prof.
Yeah. Okay, so good. So we have this then. So discounted portfolio is also a stochastic integral and it's a martingale. So now we
Wait,
want to replicate.
replicating portfolio, right?
Well, it's not,
Discounted we
it's,
already saw.
I mean, right now it's just any self-financing portfolio. And now we'll
Yeah.
construct a replicating portfolio.
Okay.
Yeah, I should probably not call this here. It's just a self-financing portfolio process right now. Okay, now to construct a replicating portfolio, we'll first need to we want to replicate this option, right? Which
Yeah.
has a pair of V of big T. Now we define V of small t as follows. And what that means is that V small t, R of small t is a martingale under P tilde. And then by martingale representation theorem, uh, it has the following representation. Right? We are just assuming that the underlying noise is just coming from the Brownian motion.
Okay. So just to get this right, so my V of small t is my expected payoff, and then I'm discounting it to that time t, right? That's all.
Conditional expectation discounted by RT. That's right.
Okay.
We just define it in this manner. This is
Okay.
the right, this turns out to be the right way to do things. So then V of t will give us the price of the option. We'll find out because this will be the price of the replicating portfolio.
Yeah.
And this gamma U is adopted. We should be careful about this. So martingale representation theorem says that any martingale will have this following representation where this density process gamma U is going to be an adapted process. Right. All right.
And to be able to use the representation theorem, we are forced in our model to assume that the filtration is generated by the Brownian motion.
Absolutely.
And
Absolutely.
does that have any implications in terms of financial theory? Like, what does that mean when I was saying, like, when
I
you were
think
applying this to finance?
I think one just accepts it. I
Okay,
think
okay,
so. Your
okay.
point is, are we putting a serious limitation by assuming this,
Yeah,
right?
yeah,
Um, I think yeah, generally people are comfortable accepting this.
okay, okay.
I've not seen the setting where okay, by assuming this, you've kind of ruled out something important in
Okay.
practice. Hmm. Okay, so now we have DRTVT is given by the following formula. And for a portfolio, we have this following relationship. In the portfolio, in the self-financing portfolio, we need to figure out what AT should be. So we can set our AT as follows, because now we know everything, right? We know gamma T, we know sigma T, we know RT, we know ST. So we chose AT as follows at every omega, at every time T. We start with V0 wealth. V0 also we know. Then we conclude. And this requires a little bit of argument, but it's very kind of, it's easily acceptable for us that if you're keeping all these things the same, then indeed RT XT will be equal to RT VT. So XT will be equal to VT for all T. So in particular, XT is equal to the option price. So we now have a replicating portfolio for the option. So price of the option is price of the replicating folio. So that's X of T. And that's just equal to V of T above. So price of the replicating portfolio and price of the option is the following conditional expectation. This is clear to everybody, right? That's how we defined V of small t. Everybody with me on this?
Yep.
All right. ठीक है, चलो, so let's carry on. And then we applied all of this to Black-Scholes equation. So Black-Scholes setting had mu t was mu, sigma t was sigma, RT was R. DST had this nice simple form, and you could express ST as this log normally distributed random variable, basically, right? Because at the exponent, you have a Gaussian distributed random variable. So because of that, the ST itself is log normally distributed. Under P tilde, we have the following relationship that tells you that ST is now log normally distributed here, but with a different mean, with the same drift. So now if you have to price an option max of ST minus K and 0, the call option, then V of T, this should be R here, still the old file. It's just the discount factor here. S of big T is distributed as follows. S of small t is known to us at time small t. So this can be a calculation that you can do. And you are telling me that you already did this last year. So this is the Black-Scholes price, right? So we'll carry on for today. So today we'll have a multivariate Grasnoff's theorem. It's exactly the same thing. Uh, So we have D independent Brownian motions. We come up with Z of t as follows. That's a likelihood ratio.
Prof, sorry, can I ask you something?
Sure.
So, if with the Black-Scholes part, wasn't the
Mhm.
entire point to come up, not just Black-Scholes, actually, even before that, the entire
Mhm.
point of the exercise was to price options, right?
Right,
We
right.
didn't want to come up with a portfolio to match it. The point was ultimately to price the option. So, if we
That's right.
already have this form for the price of the option, why are we doing this replicating portfolio thing at all?
I mean, the price we got through the replicating portfolio, right? The price of the option is the price of the replicating portfolio.
Right, right.
So
Um,
that's how
so
we,
this
yeah.
expectation of P tilde thing,
Hmm.
that is what V of small t is defined as, right?
Yeah,
So, I mean, we don't need to build an XT to be able to conclude that VT equals expectation of P tilde, all this
that's
stuff.
right. But to say that VT is equal to XT, we needed the theory.
Hmm.
And basically the theory is that price of the option is price of the replicating portfolio. Otherwise, you have an
Hmm.
arbitrage.
Hmm.
And we constructed this replicating. We just said ki VT, the way we defined it, it has this representation, right?
Hmm.
Any self-financing portfolio has this representation, but we are free to choose a AT.
Right.
So we choose a AT in this manner, then we are exactly replicating the option.
Okay, so basically the problem that we are solving is we are basically giving a tractable version of the expectation that on the right hand side.
Yeah, we are coming up with the tractable form of the option price. Basically,
Okay.
what did we do? We said, let's just choose AT in this manner, right? That's what we said so far. Let's choose AT in this manner.
Hmm.
Let's choose X0 to be V0. So
Hmm.
now we have a portfolio process.
Got it. Got it.
Now we have a complete portfolio process. Turns out that because of coefficient matching, this equation will be true, which is no big deal. What's big deal is that you have xt is equal to vt.
Right.
That tells you that the portfolio process you have exactly replicates the option.
Got it. Okay.
So
Understood.
now the value of that portfolio process turns out to be vt, and hence the value of the option is vt. So this is where
Okay.
the vt gets its sanctity.
Okay. Thanks. Got it.
Okay, so this yeah, so this is very important. Yeah. Okay, but thanks. This clarification is very important. Yeah. Anybody else? Okay, let's carry on. We don't have too many people. That's the problem, I guess, with doing these things online. Okay, let's carry on. So now we come to multivariate Gaussian. So multivariate Gaussian theorem. Uh, so it's exactly similar to the single variate setting. Now we have these, d integrals here, right? Alpha t's are basically a vector of d processes. These are all adapted processes. So alpha t could be dependent on all the Brownian motions till time small t. And this is again a normalization constant. So everybody with me so far?
So ZT is one dimensional then, right? Because when you do alpha D transpose DBT, you're getting okay.
That's correct. So ZT itself is one dimensional. Yeah.
But Prof, then how do you interpret alpha T to the power T DBT? Like you are
Alpha T transpose.
Related
Sorry, this is
transpose.
this is transpose.
yeah
Yeah,
no no
it's not
I meant
power T.
transpose only. I understood that. So what
Mhm.
you're basically saying is that you're summing up these integrals individually.
Yeah, yeah,
Okay, perfect.
that's right. And here also we're normalizing them,
Yeah, that I got.
This will also break up, yeah. So
Yeah,
now you can apply Ito's lemma to Z of t, right? It's an exponential of an Ito process in d dimensions.
yeah.
And you can check that indeed Z of t is going to be a stochastic integral. It'll be a martingale.
Yeah.
That's something you can check. We saw it in one dimension. The same thing is true in multiple dimensions. Okay. So in particular, it's going to be a mean one martingale. So I can define a new probability measure P tilde as EP of Z of t, I of A. And then Gurznoff theorem says that under this change of measure, B tilde t Uh, I guess there should be a transpose here too, right? No, not a transpose. My mistake, my mistake. This is just a vector now. This is a vector and this is a vector. So I'm just subtracting from each drift, from each Brownian motion, each component Brownian motion, I'm subtracting the corresponding drift. Or I'm adding a corresponding drift in this case. And then my B tilde T is in every dimension Brownian motion. Go ahead.
Professor, so just a couple of questions I had.
Mm-hmm.
Firstly, I'm not understanding the ZT expression.
Mm-hmm.
Um, why does it need to transpose alpha t? Like, what's the benefit there?
I mean, that's the form, right? So it's, I mean, you can kind of imagine in, if there were independent processes, you're
Hmm.
twisting each one of them separately. So it's minus 0 to t alpha t 1 dbt 1 minus 0 to t, I guess it should be alpha s here, alpha s2 dbs2. So I'm just reweighing separately each dimension. That's what's being captured here.
I see. Okay, so the d-dimensional Brownian integral is defined as the sum of the individual kind of um, individual dimensions
Yeah, I
in
mean, it's
terms.
lot of flexibility, right? So I'm allowed to reweigh every Brownian motion separately
Hmm.
by a separate adapted process. So I'm just presenting this theorem in great generality. And
Okay. Got it.
the remarkable part now is, so now this is a vector here, huh? That
Yeah.
you get, right? Yeah.
Yeah.
So I'm adding this vector component wise to each of the Brownian motions.
Hmm.
Now alpha s actually is allowed to depend upon all the Brownian motions. In alpha s is an adapted process. It
Hmm.
depends on all the Brownian motions till time s. So in that sense, it's remarkable that this process that you get is all components are still independent of B tilde t under P tilde. I mean, although I reweigh probabilities using
Hmm.
these adapted processes which can be dependent,
Hmm.
but net I get with this change of measure a Brownian motion where all the components continue to be independent.
Okay. Got it.
So that's
Right.
the Grasnoff theorem,
Okay.
right?
Professor, just a quick question.
Mm-hmm.
Yeah, so the underlying filtration right now is a sigma field generated by each of these independent random motions, right? Up to time t.
Gauri, your voice is not clear.
Sorry, can you hear me now?
Just talk slowly into the mic.
Yeah, so I'm asking whether the underlying filtration is a sigma field generated by each of the random motions up to time t.
Underlying what?
Maybe
I
you
think
can
she's asking
Filtration.
if the
that,
I think she's
that
asking if the sigma field is generated by the underlying Brownian motion
Yeah.
at time t.
Yeah, so this is, for Grasnoff theorem, it does not need to be just a Brownian sigma field. It can be more general. This theorem will still hold. So all you need is that you have this filtration f of t, and all the d-dimensional Brownian motions up till time t are measurable with respect to it. Is this
Right, yeah.
clear?
So it needs to minimally contain that. Okay.
Yeah, yeah, yeah. But Grasnoff theorem does not require the Brownian motion to underlying filtration to just be generated by the Brownian motions. That's for the martingale representation theorem. This holds even otherwise. Okay.
Okay.
So now we are going to construct a multi-dimensional market model. So there are M assets, right? And I'm going to assume that they are D Brownian motions. Right? So each asset I has a drift, which is an adapted process, any adapted process. And then it has sensitivity sigma ij to jth Brownian motion. But otherwise, sigma ijt is still allowed to be adapted. Okay, so sigma is a matrix now, basically. So if I collect all the sigma ijt, I get a matrix. So is the market model clear? So we are allowing all the M assets to be dependent on each other because they are being driven by the same source of noises. They're D sources of noises. Okay. But there's a nicer way of looking at these, these processes. So let's just define sigma IT to be this, square root of the sum square of sigma ijt, sigma ij square t. And then let's define TWIT to be the following quantity, right? So it's a weighted combination of all the Brownian motions, the D Brownian motions do I have. What do you think I can say about WIT? Any conjecture? What kind of process is it?
Is it a martingale?
It's definitely a martingale because it's just a sum of martingales. Because all these guys on the right side, these guys right here, these are all stochastic integrals.
Yeah.
So it is a martingale. But can we say more than that? All right, so let's come here. So it turns out that each WIT, the way we defined it right now, is going to be a Brownian motion. And what do we need for it to be a Brownian motion? First, we need it to be a martingale, right? But since these guys are martingales, WIT is just some of the stochastic integrals. So it's also a martingale. And it's
Yeah.
continuous. Uh, stochastic integrals are continuous. This is sum of continuous functions, so it's continuous.
Hmm.
Yeah. So it's continuously. Then what else do we need? We just need to show that its quadratic variation is equal to 1 for is equal to dt, right?
Yeah, DT.
Yeah. For it to
By
be
levies we can show. Yeah. Okay.
and then Levy's theorem tells it's a Brownian motion.
Yeah.
So we just look at this quantity, right? And basically you'll get, if you see here, these terms will square up, right? When we do dwit dot dwit, right? So what I end up getting is dt. So hence it's a Brownian motion. So each wit is a Brownian motion. Any questions on this? Okay, so let's carry on. So I can also express my stock price, my asset price I as following the following stochastic differential equation, right?
So now in some sense this would be a portfolio of like different stocks, right?
That's right, yeah. Different assets, including stock prices.
Okay.
But now, the DWITs across different assets are correlated. So it's just a cleaner way of seeing this, that, as such, this is similar to our single asset model. So typically, how we choose we arrive at a multidimensional model only when we need it, right? When we are pricing options in multiple dimensions. When we price options single dimension, then we look for a model like this. And in some sense, we have some kind of expertise and data to fit a model like this. So one kind of, uses data and comes up with parameters to get this representation for each asset separately. And then you try to work out the correlation between them, between WIT and WJT. So let's look at this. So this relationship is true. Expected value of, see, because the mean of each WIT is 0,
Yes.
right? So the covariance is going to be determined by this product E of WIT, WKT, and that has the following representation here, right? How do we
Yeah.
get this? And can you help me get this? How do we get here? How do we draw this conclusion? What do I need to do?
I mean, that's just the basic formula for correlation, right?
Right. I need a representation of WIT, WKT, where I can take expectation and get this form. So how do I get representation of WIT, WKT?
in terms of sigma.
Yeah, how do I get that?
Oh,
I mean, all I know is this quantity. I only know this right now.
so if you basically argue that, DWJT and DWIT, the product
Hmm.
of those is equal to zero if
Hmm.
I is not equal to J, because it's independent, and
But
it's equal to D.
they're not independent. They're
Uh,
all they're all linear combination of independent Brownian motions, but they themselves are not independent. That's
hmm.
the whole point. That's why we are looking at this correlation, right? Otherwise, this would have been zero.
Wait, Prof.
Okay,
Prof,
okay, of course.
Hmm.
can you go up for the WIT term?
Hmm.
No, can you go to the up slides? Yeah.
Yeah, this
So
one.
in this one we have D of any BIT multiplied by D of any other BIT. So the I think quadratic variation would just be D of T, right?
Yeah, that's what
Basically,
that's how we show that with the Brownian motion.
Yes. And then you just multiply these terms, these sigma terms with the of WK, and then you get the same thing.
Yeah. ठीक है. No, I just want you to think about what we are doing. So I'll show you what the calculation is because you need to see this once. So, I mean, this is a tool that you have. You can compute, you can apply Ito's lemma to WIT, WKT, right?
Hmm.
hmm.
Yeah.
So D of this thing is this quantity right here plus this quantity right here. Now, these are stochastic integrals, huh?
Yes.
Stochastic integral will be mean zero.
Yes.
So what will remain is this quantity right here,
Okay. Yeah. Since you're taking, yeah.
right?
Oh, and
And
then we just use the, yeah, makes
yeah,
sense.
yeah.
Yeah.
So this quantity will have these forms, sigma ijt, sigma it, sigma kjt, sigma kt
Yeah.
into dt, right?
Yeah.
And you get sum of these quantities, you get a sum here. And then when you write it in a proper integral form, then you get wit, wkt minus wi0, wk0, which is 0, plus this quantity right here,
Yeah.
plus these integrals, which in expectation will vanish. So
Yeah.
expected value of this quantity will be exactly this quantity right here. Okay?
Okay.
So I just want you guys to get familiar that, when you see these kinds of terms, you kind of have to ask yourself how Ito's identity or Ito's lemma can help you.
Okay.
Often that's a desired tool.
So one simple question. So in Gazanov's, when we say ke, let's say a Brownian motion, B and B tilde, so both
Mhm.
of them are not related to each other, right?
They're exactly
Yeah.
related, right?
Okay. Wait.
dBt is equal to dB tilde
Tilde.
t minus alpha t dt, right? In one dimension. And you have analogous formulas in multiple dimensions.
Okay.
This is like a pathwise relation.
Okay.
So, Prof, in this case, the setup, we haven't explicitly assumed the existence of a risk-free security, right?
We did, right? You mean
Oh,
in multiple dimension? Yeah, so far
yeah.
we've not.
Okay.
We'll do it now. We'll do it in a moment.
Okay.
Yeah. But that's a great point. Up till now, we've not said anything of that sort.
Okay.
All right. But you're always like exactly one step ahead. This is the next step. All right. Okay, so really we have the risk-free security as before, right?
Yeah.
So now again we look at discounted securities. Because what's the agenda now? We are again, big picture, where are we going with all this? We've defined a model for you. We have a Gazov theorem. We are going to again ask ourselves, under what conditions on this model does does the discounted securities, do they become martingale?
Yeah.
Right? That's the question that we are asking ourselves. Because
We're
if they
basically
become,
showing the initial results that we saw in the first 2 or 3 lectures now, but now in the continuous setting.
but in multiple dimensions now, because
Yeah, multiple dimensions as well.
we just
No, but
showed everything in. Mhm.
yeah. No, go ahead, go ahead.
No, we just showed everything in single dimension, right? In single dimension, we started with a model of discount rate and one risky security.
Yeah,
And then we said, okay, if we do the Gersdorff with mu t minus RT upon sigma t
yeah,
density, then indeed our discounted risk-free stock, risk-free asset becomes a martingale.
yeah,
We showed that already, right? And then we said that the portfolio corresponding to the risky security and risk-free security is also a martingale.
yeah,
So now we just want to extend that idea to multiple securities, right? We're going to ask ourselves, when do the discounted multiple securities, is there a change of measure under which these guys are martingales?
yeah,
Because then we'll be able to argue that the portfolio with these guys will also be martingale. And then we'll ask ourselves, well, with what kind of options can we replicate with these portfolios?
Mm.
Because then those options we can price.
yeah,
Okay? So yeah, we kind of did that. Well, we didn't spend much time doing this in multiple dimension, but the picture is very clean and clear, right?
yeah,
Okay, at the end of it, even in multiple dimensions, we'll have general options, and we want to exactly replicate them. And we're asking ourselves, what conditions do we need on the underlying model, you know, on our AITs and sigma ITs, so that we can exactly replicate some options.
So,
And it'll turn out that the conditions will only depend upon sigma ITs, not AITs. Yeah, go ahead.
so just want to ask, we have D sources of independent noise, and we
Hmm.
have M assets. If
That's right.
D is less than M, the intuition I have is that some of those assets will become redundant, right? That
That's
they'll
correct. Yeah.
be.
Yeah.
So, is there a also result on the sort of relation between D and M needed to have to price all options, or is that not too relevant here?
I mean, no, I'll tell you what it is relevant, but in practice, one often assumes D is equal to M.
Acha, okay.
That's a much more standard thing. You have as many sources of noises as you have assets. We'll also assume that, although I'm presenting this discussion somewhat more generally, but
Hmm.
to draw conclusions, I'm going to assume that M is equal to D. So just
Okay,
assume that for now.
okay, sure.
There could be settings, when you want to have incomplete markets, then
Hmm.
you have more sources of noise. So your D becomes more than M. That's a more reasonable kind of realistic view of the world, which is incomplete.
Hmm.
So your assets are not telling you about all the noise that there is.
Right,
Hmm.
right.
But that we won't spend much time on in this course, right? We won't get a
Okay,
chance to. But that's if you study incomplete markets.
okay.
But yeah, these are all interesting questions. All right. Hmm. Okay, so where are we? Uh, right. Okay, so this is our DRT SIT. So again, we apply Ito's lemma, RT DSIT, SIT DRT, and this term is 0. DSIT, we already know, has the following form. So that tells you that DRT SIT looks as follows. So can you see this? Basically, this term here is going to give me this minus RT that comes in here. And uh, RT DSIT, this term will basically boil down to this. I just opened up DWIT. That's a summation of sigma IJT, DBJT, right? So you're with me in this. We have a representation for, uh,
Professor, I just have a quick question.
yeah, go ahead, Gauri. But Gauri, your internet connection is not very good, huh? So go ahead.
Yeah, it's not unfortunately. Can you hear me better?
No, it's breaking up, but go ahead. I think we can barely follow. We can kind of follow. So let's see.
Yeah, just it's very small. Basically, is alpha ITD an adaptive process with respect to just that particular bounding function, or can it depend on the other convolutions as well?
I see. Your question is, can alpha, or in this case, AIs,
Yeah,
uh, they are adapted with respect to f of t, right? The underlying f of t. Is that the question?
right. Yeah,
Yeah,
yeah, yeah. Sorry,
yeah,
that's it. Thank you.
yeah, right? Okay, so we have this representation then, right? And now we'll ask ourselves, okay, when can we make this discounted process a martingale? So how do we get rid of the drift? And the tools that we are available to us is that we can just change the drift of each Brownian motion. That's what Garzanov allows us. At a later point, I'll tell you that every change of measure has this form. That's under the kind of similar assumption that we make for martingale representation theorem, when the noise is only Brownian motion. In that case, every change of measure has this form. So for now, we can kind of be comfortable that this is all we have. Okay, so these are change of measures that we can do, right? So then existence of equivalent martingale measure boils down to finding beta j t's so that RT SIT is a martingale. And that for that, what we really need, because I'm just going to plug in this, I'm just going to change this with this quantity right here, dB tilde jt minus beta jt dt. So basically it boils down to uh, setting this into an equality. So do you want to spend a few minutes thinking about this?
Yeah, Professor, could we pause for a second? Yeah, I need a
Yeah,
second.
right. Yeah, I've not added enough steps, but I can just walk you through them right now. Basically, what am I going to do? Here, let's just rewrite this as dB tilde jt minus beta jt dt, right? Then this will remain, and beta t dt will be multiplied by sigma jt rt sit, and we want to choose our beta t in such a manner that this noise cancels. So we want a1t minus rt, amt minus rt to be equal to this quantity. In that case, our discounted asset price process is going to be a martingale. It'll be a stochastic integral. So everybody with me on this?
Yes.
Right. This is what we need. And in shorthand matrix notation, we just need this vector a bar t minus r bar t. R bar t is just a vector with each entry rt is equal to sigma tilde t. Sigma tilde t is just a matrix of all these sigma ijt's into beta bar t. So we just want a solution to this. And this is where Siddharth's question becomes relevant. What we'll do for now, and that's typically done, we'll take m to be equal to d. In which case, all we're asking is, for the solution to exist, we need sigma tilde t to be invertible. If it's invertible for every t and omega, then indeed we can take our beta bar t to be the following quantity. Right? So sigma t tilde t being invertible ensures that we have an equivalent martingale measure. But essentially what we need is we want this equation to hold true. So even if m is not equal to d, what you're really looking for is this equation to hold true. So that would be a more general way to write the results. But for now, we're going to just assume that, okay, with sigma tilde t, this is a matrix of noise. It's our mathematical model that we choose, right? We choose our mathematical to fit the data. But suppose we choose it in a manner that sigma tilde t is invertible. We impose that restriction. Now you can test whether that restriction is a reasonable restriction given the data, or whether you're making glaring mistake. If you're making glaring mistakes, okay, then you're in trouble. Then this modeling assumption is not a good one. Okay, but we are going to assume this, and then once we assume this, then we have this discounted asset price process for each asset SIT is a stochastic integral. This you can see. because all these drift terms are going to cancel then, this term is going to cancel with this guy right here. So what you're left with is the remaining integral here. And that's exactly what I'm showing here.
Sorry, but can you show this entire slide once, even the beginning?
I see, yeah. This one here?
Yeah, thanks. This one. Are these slides uploaded yet, Prof, on the website?
I'll do it. There's some typos I want to remove, but after
Okay.
today's lecture, I'll upload them, yeah.
Okay.
ठीक है. So we've got that if indeed our diffusion matrix is invertible, then we have this risk neutral change of measure. But this is very interesting. So this analysis, I'm going to again be a little bit quick on this, but you should get the idea that indeed, if this was not true, if this does not have a solution almost surely, right? So on a positive probability set, it does not have a solution, then indeed you have an arbitrage. So is this kind of clear, the statement that I'm trying to make? That this is necessary and sufficient for this to have a solution, for equivalent martingale measure to exist. Okay, so how do we see that? So I'll just give you some ideas in this direction. I'll take S tilde T to be a diagonal matrix. This just helps me notationally, whose ith entry is SIT. So S tilde T is a diagonal matrix. First entry on the top of the diagonal is S1T. Second entry of the diagonal is S2T. And the last one is SMT. You're with me on this, right? So the big point I want to make is that this does not have a solution, corresponds to this guy here, does not have a solution. So how do we do this? I guess I should probably write this down somewhere, right? So let's just do this in 2 dimensions. So we have A hat A1T. And what were we saying? Minus RT. So A1T minus RT, A2T minus RT is equal to sigma 11T, sigma 12T, sigma 21T, sigma 22T into beta 1T. So this does not have a solution. There's no beta 1, beta 2 which satisfies this, right? I can also say this is same as saying that A1T minus RT into S1T, A2T minus RT into S2T, because S1 and 2 S2T are all strictly positive. And then I have S1T into sigma 11T beta 1T plus sigma 12T beta 2T and then S2T into sigma 21T beta 1T plus sigma 22T beta 2T. Right? So this has a solution if and only if this has a solution, right? I'm just multiplying both the equations by S1T on both sides and by S2T on both sides for the second equation.
Professor, have we explicitly forced the price processes to be non-zero? I mean, isn't it possible they could drop to zero at some point?
I think, yeah, so I'm assuming right now that S's are strictly positive.
Oh,
Yeah. Mm. Actually, strictly non-zero. That's all I really
right,
need.
right.
Mm. Yeah. Okay. So, yeah, this is just, helps in explaining something slightly more easily. Okay. So I'm going to assume that this guy does not have a solution, which is what I just showed you. S tilde t is our diagonal matrix on both sides, right? So for it not to have a solution means that, uh, in the span of, I guess, columns of this guy, this vector does not lie in this span, right? Because I'm looking at all beta t, which are combined in these columns. So that means if there was a theta t which was perpendicular to these columns, yeah, then that theta t will make a non-zero angle with S tilde t at minus rt, right? If something
Um,
doesn't lie in the span of vectors, right? Uh, so then, then if there's any vector in the null space of that span, that's theta t, it is going to make a non-negative, non-zero angle with the with this vector right here, which does not lie in the span. Is this clear?
Sorry, Prof. I had a question.
Yeah, yeah.
So just to be clear, you're saying that we view ST sigma t beta t as the
Uh-huh.
linear combination of the columns of ST sigma t weighted by the beta t's.
Yeah,
And the point is that if there doesn't exist linear combination which is equal to sort of this AT minus RT
yeah.
thing,
Yeah, let me just give
then
some.
there is sorry, yeah.
Yeah, no, I agree with you. I'll just give some more notation just to make this point. So
Sure.
let's just call this as, what do you want to call it? Let's call this as vector x, or let's call it y. I think y is something we see more often. So y is equal to a times x, right? So we're saying y equal to ax has no solution, right? Uh,
Hmm.
so that means in columns of x, if I look at the space spanned by columns of a, I don't see y there, right? So then if I have a theta which is in the null space of a, so theta transpose A is equal to 0, then the theta transpose Y is not 0, right? So if Y equal to X has no solution, implies this quantity. So, Aman, I see that you become quiet. Are you with us?
Yeah, Prof.
Okay, good. Yeah, just, okay, so that's all I've done here. And now the point is this theta that I've come up with, right? It's non-zero. Uh, or at least on some omegas of positive measure. Now, sometimes it's positive, sometimes it's negative, right? Um, Suppose it's all negative, then I can just take minus theta and get this to be positive everywhere.
Yeah.
Suppose it's positive sometimes and negative sometimes, then wherever it's negative, I'll set that theta equal to 0. So then again, I get this relation to be positive always, whenever it's true. Either theta is 0 or whenever it's true, it's positive. But such a theta will exist with positive measure. Okay? Because I'm doing this omega t by omega t.
So Prof,
Mm-hmm.
so I just want to clarify like the linear algebra behind this for a second.
Yeah, yeah. Hmm.
So I get that we're saying that okay, ax equal to y doesn't have a solution means A
Hmm.
is not full rank, which means the columns of A do not span the whole space, which means there's some theta which
Mm-hmm.
exists which is linearly independent. We can
Right,
orthogonalize that theta to find some new theta which is orthogonal to the columns of A. That is what the first kind of equality to zero is. Right.
right.
Um, can you explain once more where the second one is coming from? Why is it also orthogonal to y.
No, it's not orthogonal. It's making a positive angle with the,
Sorry. Yeah.
yeah,
Oh,
yeah,
okay.
yeah.
I see.
Because if it's making a negative angle, I'll just set those thetas to be 0. Now you can say that for all thetas it was making a negative angle. Then I'll just take
Mhm.
minus theta instead of plus theta.
Okay.
So I get
I
this
see.
to be true.
Acha. Okay.
ठीक है?
Yeah.
So I've got such a theta now. I've got a theta which is orthogonal to these guys. See, the point is I'm going to construct a portfolio with this theta. And I'm going to construct a portfolio in such a manner that all the noise cancels. Right? And then I'm going to argue that I still have a drift which is positive. I'm still getting returns from it without any noise. So that's going to give me my arbitrage.
Right.
That's where I'm going with all this. So everybody with me so far? Kind of, sort of?
Yeah.
So recall that again that, what we have is that DRT SIT is given by the following formula. We've done this already. Now I'm going to construct a self-financing portfolio. For self-financing portfolio D of, theta T I RT SIT. So theta Ti is the amount I invest in IH security. And this is just the discounted value of this portfolio. Because it's a self-financing portfolio, I get this to be summation theta Ti DRT SIT. That's like the argument we had done earlier for self-financing portfolios, that the only change happens because of change in the risky securities. So this is, I'm jumping a bit. I could probably give you more steps, but I'm just expecting you to believe this. Because we had seen this in single dimension. I'm saying the same thing is true in multiple dimensions. Right? And now let's look at this quantity right here. So it's summation theta I AIT minus RT SIT dt, and this quantity right here. And the point is this quantity right here, because of the way the thetas are defined, because theta satisfies this property right here. So theta T I SIT into sigma IJT for each j, when I sum up over I get 0. That's what this quantity here is giving me basically. Right, this boils down to summation theta T I S tilde T I sigma IJT for each I is equal to 0. No, for each j is equal to 0, sorry. Yeah. So this quantity is going to vanish. Are you guys there?
Yes, Prof. Yes.
Yeah.
Okay. Chalo, you'll have to, there are more steps needed to make this clear. We can maybe take it offline, but you kind of get the flavor of things that, this was our, when you have self-financing portfolio,
Hmm.
the change is basically given by theta Ti into D of RT SIT.
Okay.
I mean, the nuance which I'm not mentioning to you is that if you think of SIT as money market,
Hmm.
then RT into the money market is just a constant, and D of that is equal to 0. So in the asset that I'm showing you, there's no money market asset, uh, but basically the money market asset ensures just investments to risk-free security to make the portfolio self-financing. You just change the investment in the money market account, you increase or decrease it to ensure that you always have a self-financing portfolio. But the money market changes will not really, yeah.
Can you repeat this point? I didn't fully get that.
Yeah, no, this I've not developed it properly. So, but I just want to still make this point ki, you know, if I look at RT into MIT,
Hmm.
this is the money market account,
Yeah.
that's just equal to 1.
Yes.
So D of that is going to be equal to 0,
Zero.
right?
Yeah.
So I've not included that term here
Okay.
because it's 0,
It's zero. Yeah.
but it's the money market account which ensures that your portfolio is self-financing. Whatever changes happen in the risky securities,
Hmm.
balanced by that by the investment in the risk-free security. So essentially, you still continue to have a self-financing portfolio.
Wait,
So
but
this
that term is going to zero. So how is it still adjusting my investments?
meaning I can add that to this equation here, and nothing will change.
Yes.
This will still be the same.
Yeah.
So this equation is valid.
Okay.
Right? So that's what I'm really saying. And since this equation is valid, so let's look at the right-hand side. The
Hmm.
right-hand side is the following quantity,
Yeah.
and in the right-hand side, the diffusion term is equal to 0. Because theta ti sit summed over I into sigma I jt for all I is going to be 0.
Hmm.
So the coefficient of dbjt is going to be 0 for each j.
Okay.
So this term is going to vanish. So really what you're left with is the following quantity. This
Just the
change
drift
here
part. Yep.
is just the drift part, and that we've argued is positive here. That's this quantity that's positive.
Yeah.
So then your discounted portfolio is still making money. Discounted portfolio should not be making money.
Yeah. It should be a martingale.
Huh, huh. But in this case, it's deterministically making money with
Hmm.
with positive one probability.
Hmm.
So that means that the undiscounted portfolio is increasing at faster than risk-free rate of return
Yeah.
without taking any risk. That means you have an arbitrage.
Yeah.
So that's the broad argument. Siddharth, is that okay?
Yeah, I mean,
Can
so
you?
I'm seeing why
Yeah.
like the second part is zero, the
Hmm.
second term is zero, and I understand that the first term may that inner product will be greater than zero.
Right.
You're saying that with that condition, it means my portfolio process XT is
Hmm.
not a martingale, which means arbitrage.
Well, what I'm saying is my discounted portfolio process is
Hmm.
still making money for sure. It's making positive money as time goes by.
But that
So
should
if
Yeah,
not.
the discounted portfolio process is making positive money, that means the portfolio process is making money at a faster rate than the risk-free rate.
Yeah.
That means I can buy at risk-free rate and invest in this portfolio and sell this portfolio and
Yeah.
make money out of nothing. That's an arbitrage.
Yeah. But that should not be happening now. So like
So
our.
that's the point. So whenever this is not true,
Hmm.
then I have an arbitrage. So no arbitrage condition means that this has to be true.
Okay.
That this should have a solution. In particular, in M equal to D setting, sigma tilde T should be invertible, has to
Yeah.
be invertible. Yeah. So that's the point being made. And when it's invertible, then we can actually find beta tilde T twists beta bar T as follows.
Yeah.
And then our discounted portfolio process does become a martingale.
Yeah.
Hmm. Okay. Sorry,
I
Prof,
think
can
I
I ask
got.
one question?
Yeah, go ahead, go ahead.
So we concluded that if let's say XT is the discounted portfolio process, we
Mm-hmm.
essentially showed that DXT equals RT times the inner product of theta and STAT minus RT.
Right, right, right. Yeah.
Yeah. And we said that the inner product part is greater than zero. So essentially
Mm-hmm.
we've shown that DXT equals RT into something greater than zero DT.
Mm-hmm. Mm-hmm.
But it's not greater than one necessarily, right? So I mean, I guess I'm not understanding why that implies that it's making more than the.
Yeah.
Oh, because we already discounted it, you're saying. We
We've
already
already
discounted
we've
it,
already
and yet.
discounted it. Yeah.
Okay, gotcha.
Yeah. So I should add one more equation here to show that what this means is that the process summation theta ti sit, that's growing at faster than risk-free rate and has zero risk.
Okay, got it.
And
Yeah,
but that
no,
can that's this applying Ito's lemma.
okay, okay, thank you.
Uh, so hence you have an arbitrage. So it's a little bit of a quick argument, but you pretty much get the flavor of it though. That if you can't come up with this change of measure, then you can come up with theta, which exactly you can come with a portfolio which exactly cancels risk, and you can tweak it in a manner uh, that it gives positive returns, and that leads to an arbitrage. Okay, shall we carry on?
Yeah.
Okay. So the portfolio makes money while taking zero risk. That was in the earlier case. Then you had an example of an arbitrage. Okay. So risk neutral measure exists if this relationship is true. Has a solution for each t. And in that case, the discounted securities, each of the discounted securities are stochastic integrals. So these are martingales. Where again, this B tilde JT is uh, just a kind of a shifted version of the original Brownian motion. And with this as your likelihood ratio, you assume um, you reach the new change of measure. You achieve the new change of measure P tilde A. Right? I mean, I've been kind of bad with notation. Somewhere I'm calling this P bar. I should be consistent. Okay. Now we are going to assume that again that such a beta t is possible, and now we'll argue that with that the portfolio process, when discounted, will also be a martingale, just like we did earlier. So a portfolio process, I'm investing alpha IT in the ith risky security, right? And the remaining wealth that I have, xt minus summation alpha IT SIT, I'm investing that in the money market at the risk-free rate security. So this is the equation that dxt satisfies. So now you can see just by plugging in values that drtxt is going to be summation I equal to 1 to m alpha IT drt SIT. This is the same calculation that we did in single dimension. So it extends analogously. Right? I mean, I can just open this quantity up here. I can open this quantity and show that these two are equal. And now, once I do all this, I have I have following relationship that's holding. So I know what DRT SIT looks like. It's a stochastic integral. So I plug that in here. So this is basically DRT SIT, but now it's weighted by alpha IT for each asset, because portfolio has alpha IT amount of risky security. So right. I just want to see if I can say something interesting. I think this should be fine. So I've just plugged in this right here. So I get my DRT is simply this stochastic integral. Remember, RTST is given by the following formula. So I have now concluded that when the risk neutral measure exists, when those beta twists exist, when the sigma t is invertible,
Mhm.
in that case, any self-financing portfolio process, when discounted, is a martingale. Hence, under P tilde, yeah.
Professor, so we showed that in the previous part that if that there's no beta t that satisfies that equation, we
Mm-hmm.
can come up with some arbitrage. Is it an equivalent condition? I mean, if there's no arbitrage, then, sorry, if there's arbitrage, then that necessarily that equation is unsolvable.
So let's see. So we said ki whenever those set of equations don't have a solution, we have an arbitrage,
Hmm.
right?
Yeah.
So, so right. So then no arbitrage means that those equations have a solution, right?
Yes.
Right. Yeah. So no arbitrage means that those equations have a solution. And now we are saying when those solutions have a solution, then also we don't have an arbitrage. That we'll complete right now. So we are saying now that suppose those equations have a solution,
Mhm.
Hmm.
so our sigma t is invertible, then
Mhm.
every self-financing portfolio process is a martingale. That's where we come. And now
Oh.
we'll argue that that means that there's no arbitrage.
Hmm. Got it. So this entire thing is just proving that
Yeah.
equivalence.
That's right. Yeah.
Oh.
So whenever there is a martingale, so this proof is quite straightforward. That whenever you have a martingale measure, basically this neutral measure, then there
Hmm.
cannot be an arbitrage.
Okay.
I mean, the tougher direction is to show that the no arbitrage principle applies existence of martingale measure. So let's do this. So this is what we want to show now. That's your point. We want to show, again, you're exactly one equation ahead. Under this neutral measure, there is no arbitrage. As before, I mean, okay, as we showed in the discrete finance lectures. So for this purpose, let's define what an arbitrage is. Arbitrage is a portfolio process XT where you start with zero wealth and then at time t, you have positive wealth, non-negative wealth with the probability 1 and positive wealth with positive probability. So that's a reasonable definition of an arbitrage. Everybody agrees?
Yeah.
Yeah.
By the way, Aman, do we have people watching the live stream or not really?
I think there are 2 to 3 people watching the live stream.
I see. So yeah,
The thing
this
is, today there are like multiple classes for
I
uh,
see.
yeah,
Makeup class is going on.
yeah, for all of the holidays.
Hmm.
Yeah.
Chalo, just one sec then. Right. Hmm. Right. So we got this, right? Uh, okay. So this is the definition of an arbitrage. But now we have that our portfolio process, discounted portfolio process, a martingale, right?
Yeah.
So, but if indeed there was an arbitrage, then this would be true. This quantity is zero and this quantity is positive because RTXT is positive with positive probability. So it's a non-negative random variable which is positive with positive probability. Its expectation is going to be positive.
Yeah.
So if there's an arbitrage, then the discounted portfolio process is not a martingale. So given that the discounted portfolio process are martingales, there is no arbitrage. So under risk neutral measure, each discounted portfolio process is a martingale
Yeah.
and hence there's no arbitrage.
Yeah.
So basically it's just the two of you holding fort right now. All right. ठीक है. But I guess This just means we'll get 4 or 5 views of the videos later. Okay. ठीक है. So you're with me now on this, that if indeed there's a risk neutral measure, then there cannot be an arbitrage,
Yeah.
right? Because arbitrage implies this property. We defined what an arbitrage means. You know, when I say this, x0 and this can't happen, then I'm also saying that uh, r0, x0 is equal to 0, and this cannot happen, right? Because RT is strictly positive.
Yeah.
So indeed, if there's an arbitrage, then for that discounted portfolio process, this must be true.
Prof, your screen went.
Yeah, it again wants me to say that I trust. When prompted, select trust. So is it back?
No, not right. Yeah, it's back. Yeah.
Yeah. Okay. So how are we doing on time? We have 9 minutes left.
Yeah, 9 minutes.
Right. Okay. We should just finish this course in 9 minutes and have exams. Okay. When can an option be attained? So we still have to talk about. So right now we've just basically argued that no arbitrage implies risk neutral measure, and
Yeah.
risk neutral measure implies no arbitrage.
Yeah.
I mean, somewhat comprehensively, we made this argument. Now, suppose you want to price an option V of t in multiple dimensions. We haven't done that so far, right?
Yeah.
And we're going to assume now that the risk neutral measure exists.
Prof, why are we using a filtration here? Like, not a filtration as in like the.
I mean, we always defined our option payoff as a random variable. And this is just saying that it's known to us, its value is known to us at time big T. So it's
Okay.
measurable with respect to calligraphic FT.
Okay.
Random variable you have to define with respect to filtrations. ठीक है. So now we want to kind of figure out whether we can construct a replicating portfolio, right, which prices this.
Yeah. And Prof, E tilde is my risk neutral measure, right?
That's correct, yeah.
And that's why we don't have the divide by the discounting part here.
No, वो तो ऊपर यहाँ पे आ गया. This is exactly to a minus 0 to t ru du, and in the denominator I have e to the power minus 0 to small t ru du. So I've just brought that upstairs.
Okay.
So yeah. So I mean, in the risk neutral measure, we needed to divide, and we've done that. So let's define Vt as follows. So this again ensures that RT-Vt is a martingale, just as before.
Yeah.
RT, recall, is just e to the power minus 0 to t rs ds.
Yes.
Okay.
Yeah.
So now what I've not written down here is the multi-dimensional martingale representation theorem. But basically, it's analogous to the single dimension one. All it says is that every martingale, when you restrict your sigma algebras to be noise by Brownian motion, then every martingale is a stochastic integral.
Okay.
So RT-Vt will have the following representation.
Okay.
Right?
Yeah.
Okay. So now we have to kind of ask ourselves, okay, can we replicate this option? Can we construct a portfolio process which matches this? That part is clear, right?
Yeah.
We are given an option V of big T. From that, we've constructed all of this. This martingale representation theorem was useful for coming up with this representation. All right. So this is what we have above. And we've already argued that every portfolio process looks as follows. Right? It's a stochastic integral of the following form. Alpha
Yeah.
I t is the investment I make in the IH security, the number of IH security that I have. Okay, so now basically I have to match these two, right? That's what it boils down to, coming up with a replicating portfolio process. So I need x0 to be v0, and I need gamma jt
To be
to
this
be
one.
the corresponding term
Yeah.
for the gth component of Brownian motion.
Yeah.
alpha IT, RT, SIT, sigma IJT.
But Prof, how would we compare the coefficients? Like on the top, it's just B tilde J of T, and in the bottom, oh, it's D. Okay, my bad, my bad, my bad.
Yeah, we'll just set them all equal.
Yeah, yeah,
We'll choose alpha IT cognizant of this in
yeah.
such a manner that we have a complete match,
Makes sense.
right?
Yeah.
Okay. Okay. So we need to solve this thing here.
Yeah. Now we need to show that the solution exists.
And this is, I've just taken RT on the other side. This becomes a vector representation. And this is sigma T transpose into alpha T S bar T. Alpha T S bar T, alpha bar T S bar T, which is, I just mean this way. So rather than keeping S bar as a matrix, I've just defined this notation here.
Yeah.
So I want this to be solvable. I want to be able to solve for alpha T,
Hmm.
right? And again, you can see that I'll be able to do this if my
The
sigma T transpose is invertible,
invertible matrix. Yeah.
right? In that case, alpha bar T, sigma S bar T is given by sigma T transpose inverse into RT inverse gamma bar T. So indeed, if my sigma T transpose inverse exists, then every option I can price. I can replicate every option.
Hmm.
So my market is complete and every option VT can be attained. Okay. So this is the last slide for today. Recall that equivalent martingale measure exists if I have a solution to these equations. If market is complete,
Sigma T is
then
invertible and
sigma T
the
is invertible.
yeah, yeah. Makes sense.
And if sigma T is invertible, that means this usual measure is indeed unique.
Prof,
Okay,
should I,
so
if I
yeah,
want,
yeah. So consider a market model that has residual probability measure. The model is complete if and only if the residual measure is unique. So we'll do this properly next time. But basically, if sigma T is invertible, then I can price each and every asset in the market. And if I can price each and every asset in the market, then sigma T is invertible. So that's what I want to show. So then my market will be complete. Okay, so we are again brushing aside lots of technicalities, but you get a flavor of the underlying ideas, at least some of the ideas. So let's come back to this point next time when we meet.
okay.
Because so we'll start by just reviewing this multidimensional stuff, at least the completeness part in some depth. ठीक है